Good afternoon. I'm the WWU team lead of the Digital Manufacturing Challenge. Now I'd like to introduce you to my teammates who all contributed to the project.
Uh, that was Devin. My name's Ryer. I was design lead for the project.
Hey, I'm Bob, and I handled a lot of the manufacturing and process decisions for our project.
Hi, I'm Victor. I was the treasurer and I also helped make sure that we would be able to create a prototype to make sure that our design would work.
Awesome. And I'm Devin. Thank you for joining us today for today's presentation. 2020 theme for the Digital Manufacturing Challenge was Sustainable Communities, and our project was titled Wind Energy Kit. And the WWU team project was the overall winner of the Digital Manufacturing Challenge. Here it is, the title slide. Go on next here. So this kit, it's a source of power amid a disaster. So when disaster hits, electrical energy, is essential for communication, which could be cell phone, any type of device, walkie-talkie, or to communicate. And oftentimes, the energy infrastructure is damaged. Energy solutions are absolutely essential to have. So this is why we came up with this project idea. And wind energy can be harvested nearly anywhere in the world, and vertical turbines can be made ultra-compact. Wind turbine kits can be easily shipped to areas affected by disasters as well for immediate relief, or they can be produced beforehand. Next.
Alrighty, so functionality and the durability of our design. So once we had concluded that wind power would be the most practical energy source for us to utilize, we began considering, a vertical versus a horizontal wind turbine blade. So a horizontal turbine is generally unfit for smaller scales and lower altitudes, which are the kind of conditions that we would most likely be implementing our design under. So then we started looking at vertical wind turbines, and vertical wind turbines will function regardless of your wind direction, as they can take an oncoming gust from any direction as the axis is vertical. And it also has the capability of starting under much lower speeds. So allowing the design to be open source, which was another design decision that we had made, allowed users to print their guides for the vertical wind turbine under any kind of circumstance that they would like to, which definitely helped out when it came time to print your parts for the wind turbine given specifically for your specific situation. Next slide.
So the cost, benefit, and value here is that these turbine blade guides, they're 3D printed, and the STL will be available online, easy access. And the guides can be scaled for any size of the turbine, whether it's a small portable one or even larger turbine that could go on top of a rooftop. They can be easily scaled for the purpose. And the plastic sheets used as the blade itself are inexpensive and easy to cut the shape that fit around blade guides. All the parts and materials for this kit can be easily replaced with other materials for whatever particular application there is. Next slide.
So some of our biggest concerns. So some of our biggest concerns when looking for a manufacturing process was the potential size for manufacturing. There are some additive processes that do not allow you to print on a very large surface area. So that was one of the reasons that we decided ending up going with FDM printing. Another reason that we ended up going with FDM printing was that we wanted to be able to have the capability to print with polymers and various plastics that would have a high weatherability rate, and would also have the capability to be able to have its material changed no matter what printer you're printing on. So if you're at home and you only have the capability to print with PLA, you could go ahead and you could print with that given material. If you have the capability to print with, a more expensive, high-end engineering plastic, you can also do that. Then we began looking at various materials, and two of the most common materials that we found that people will generally end up printing with is PETG, which has a very strong weatherability and strength quality to it, and then also PLA, which is a very common printing material, and it is capable of being industrially composted over the course of about 1 to 3 months. So if you're making your wind turbines with this material, and you're printing them on a very large scale, we would highly suggest using PLA, as you could then compost it once its life cycle has reached an end. Next slide.
All right, so here we see the turbine in its final assembled configuration. The turbine is modeled after Savonius design, which dates back to 1922. We decided to go with a helical design due to the fact that we were able to reduce pressure pulses caused by, if the turbine is just extruded in a vertical fashion with no twist, you get pulses of wind, and it negatively affects the efficiency of the turbine and increases loading. So the fatigue rate increases, and you decrease the lifespan of the turbine. The helical design is optimal for generating energy from low speeds. Generally 2 to 10 meters per second is a good operating speed that we've decided on. These are conditions that you can expect just about anywhere in the world, usually near the ocean or mountainous regions. You can see plastic sheets that are shaped and secured over the blades, shown in green. The blades are in green, the sheets are clear here. They're easily manufacturable using laser cutters, or if you have a printer, you can print up a profile and cut them out pretty cheaply. And then essentially the blades are just driven by the drag forces of whatever wind is hitting it. And like Rob said before, wind from literally any direction will power the turbine. So it's a pretty good design. Next.
So the marketing of this product will be very important, since we all know that electrical power is an absolute necessity for communication devices, especially during a natural disaster. So this wind turbine kit would be available for immediate shipment to these affected areas due to the ability to 3D print and to use materials that are more readily available. Through marketing as well, donations from engineering companies would be highly encouraged to promote more charitable acts as well as good advertising for these companies. And because you can print them with PLA, and as Devin stated beforehand, the STL file would be readily available to the masses. So now anybody with a 3D printer could actually prepare themselves before the natural disaster hits. And now people can now work with each other, and it creates now this open-mindedness of cooperation and community help. Next slide, please. And now to the social and environmental impact of this. By manufacturing this device, entire communities would be able to gain the access to a reliable source of power through clean, renewable energy. As we come into the 21st century, this is something a lot of companies and a lot of engineering companies are starting to push for. And with this design, and because of the safety and to being able to help the masses during these disasters, this now becomes a good product for the families that are affected by these natural disasters. This would also encourage the communities to come together during those tough times, as I stated beforehand. And because PLA filament is a good material, as stated by Bob, since we can now actually compose it, it wouldn't cause a negative environmental impact. Next slide, please.
So once we were completed with our design phase, we decided to go with a prototype. We made a 3 to 8 scale prototype that's essentially, it's 9 inches in diameter. The full scale would be roughly 2 feet diameter. We constructed and manufactured all the components in the Western Washington University Makerspace, which has 3D printers and tools and just about anything you need. Once assembled, we ran a test, and the turbine was basically just placed under a constant wind condition. We used just a standard box fan, and we were able to achieve RPMs of around 200. And this is, again, is in multiple orientations, including from directly underneath and directly above the turbine and everything in between. It's pretty impressive, honestly. It's just basically it's 10 printed blade guides shown in gray here. We printed them using PLA plastic, and then 2 laser cut vinyl sheets. And the pattern here, which I referred to before, was created using SolidWorks. The entire design was done in SolidWorks due to the fact that it's got a really good set of tools for creating helical structures. And once we had the helical guides or the turbine blades rather, we were able to use a surface flattening algorithm to generate the pattern shown below. Yeah, and this one was laser cut. And that's it. Next slide.
Before finishing our presentation, we'd like to give a couple of special thanks to Dr. David Gill, who was the academic advisor to the student chapter at Western Washington University. We would also like to thank the engineering faculty at Western Washington University for all their support in teaching us the new 3D printing technologies that companies use. And as well, we would like to thank the Western Washington University Makerspace for allowing us to have the access to the tools and resources we needed to create the final prototype.
Thank you.